about the subject, kinetic energy cascade from surface drifter observations in the Walvis Ridge region and the Benguela region. This is mainly about, so in the TRR there are 3 cruises. 2 have already taken place in Benguela region and Walvis Ridge region, and there will be a 3rd in context with SWAT, satellite mission, and the collaboration with Draeger-Dietel, and recently with Jochen Horstmann from a partner institute of the TRR. And I should also mention former collaboration from first phase, Kerstin Jochemsen and Gualtiero Badin. So this inverse energy cascade is an important feature in fluid dynamics, and it was Krejcik who showed that due to the constraint of energy and entropy, there shall be energy flux towards larger scales and entropy towards smaller scales. And there are numerics and laboratory works who show the corresponding spectra, but for real flows in oceanography, that is not such simple. And our motivation is to explore the concepts of inverse cascades in quasi 2-dimensional turbulence to real geostrophic flows. And the talk will be that I first will explain the velocity structure functions, which are very common in atmosphere, but not so much in ocean, and have some constraints. I will talk about the first cruise, Benguela region, where we have 2 typical behaviors. First, a very wild drifter release in the upwind zone, which is a perfect candidate for this structure function formalism, and then a filament release in the filament, where they stack together, and this is strongly connected to what Yan Qing presented in the morning, and also scale-dependent Rossby numbers. On the second cruise this last year, Sonnet 1 was in the Walvis Ridge region, and there we had the different drifter types, and we have a new deployment strategy. Finally, we compare the third-order structure functions for Benguela and Walvis Ridge, and for the different drifter types, and come then conclusion and outlook. Here is a typical picture of a velocity field in the region. Here, Angular region, velocity derived from sea surface height, and it's also the region of our second release of drifters. You can see it's more or less closely beyond Cape Town. So coming to what quantities we are measuring. If we zoom into the velocity field I showed you before, we can take 2 points which are separated by distance r. At each point we have a velocity. We think of an Eulerian measure, so fixed stations where the velocity changes. And we can calculate here the difference between the 2 velocities, and can also project it on the separation vector. And what we are interested is the velocity difference as it evolves in the average with increasing separation. If we would have very large separations, the 2 points would be uncorrelated, reveal uncorrelated velocity, and then this quantity, for instance, the mean the second order structure functions, the mean square velocity difference would be constant for large distances, because there's no correlation anymore for large distance. But if we have turbulence, turbulence imposes correlations on the system. And that leads to a typical scaling of these structure functions with the distance between the points. There's, for the second order structure function, there's a connection to the spectra. It comes to this formula with a Bessel function. Don't go into detail because we are mainly concerned with this third order structure function, where we average about all pairs with a certain distance. And it's Kolmogorov who showed that this third order structure scales with R, so linear with R, and the proportional constant is the energy transfer rate, energy per volume and time towards smaller scales. And it was Kretschmann who showed that there's this inverse cascade, so energy towards larger scale. And usually it's shown that we take the third order structure function divided by R, and then we should have a plateau either in the positive sign part or in the negative part. And from this we could derive a forward or inverse cascade. So this idea is an Eulerian measure, but in the ocean that's quite difficult because we have grids, but the resolution is not so great. It's satellite data barely resolves the Rossby number. We have better data, but they only see few regions, or so this method is not so easy to apply in the ocean. That's why we look at Lagrangian drifter and derive the velocity from these trajectories of Lagrangian drifters and treat them as if they would be scattered point Eulerian measurements. That has been done, for instance, here from Belvada to derive the energy distributions on different scales, or spectral fluxes, or Ambrosio. And also Han Van gave me a very nice talk on that yesterday. But of course, this method has some caveats, like there are small scale biases because the drifter are trapped in converging structures. This is something Pearson analyzed. And we have also what I call time-space correlation, because you have a drifter bunch, you release it in the ocean, and in the beginning it measures the small scales at small times and in small scales, and larger after some times it measures the larger distances. So it's not measured simultaneously. And if you have a mean flow additionally, it's even worse. So that's why we developed for the second choose another deployment, deployment strategy, which tries to adopt different spatial scales simultaneously. This is a first cruise Benguela region, and you can see that here we released the drifter at the temperature gradient of the filaments. This is such finner-like structure of upwelling water. And you can see it's very different. There is this red bunch who explores the region nicely, follows the single currents of the upwelling zone. And there's this blue bunch which is trapped in a filament. So that would be not a good candidate for applying structure function methods. And what we deploy are deep drifters, expensive drifters, like there's a buoy and a drogue in 15 meters depth. And it's so that the drogue follows the currents and the buoy just follows the drogue and communicates with the satellite. So these are our results for this so-called northern release, the red one. Here we have the third order structure function divided by S, and the curve shows a plateau in the positive part. That is, it shows inverse cascade, and from the plateau one can derive the energy, the transfer rate. And it's surprising because it's only a handful of drifters, of 15 drifters, 12. But one has to be aware that we look at each combination, all pairs, and it's a very high temporal resolution. So we have 500,000 values, although we have only 12 drifters. But also the entropy cascade is met here. And interestingly, we could combine this energy transfer rate with former work, namely in turbulence shows up also in kinematic properties, like if you look at pairs who separate in the course of the time and you average about all pairs, then you have specific temporal dependence, like in the beginning when the distance is smaller than the typical Eddy size, there's an exponential growth. Then there's T-cube law, famous T-cube law of Richardson. Here we have a 2/3 because we took the root. And finally, if the distance is larger than the typical Eddy or largest Eddy, then we have a diffusive system. So as quadratic. And we can go with this energy transfer rate into the formula of Richardson, and we get C, which is close to the one measured from Julia and in laboratory. So, okay, this is the other bunch which we analyzed, and yeah, we have here we roughly speaking, we look at triplets and how they can change their size. Okay. And we can derive from this vorticity divided by F, so Rossby number, and then we have signatures of strong hagiostrophic contributions. And if we then have another measurement like here with one Yangping, like the scanfish and the wind, they can help to interpret what instabilities are there, and this Yangping could explain better. And so, and also we can look at the separate bunches of drifters, and we see there's much more hagiostrophic activity within the filament, and until the Rossby radius, roughly, there after that it's similar. So, so the net cruise led by Marvin, Walter from Bremen, we had gave us the possibility to have also Carthy drifters, which have 50 centimeters depth and radar. And I go not into detail. What I want to say is we try to avoid time-space correlation by deploying the drifter in a way such that, like an fractal, maybe some remember what is the fractal, like you have all kinds of scales simultaneously, because of course it's only 2 iterations fractal. So we have here are the shallow drifter, and the big spedards are the deep drifters, and they are all triplets. And okay, now I will show the sorry. So this is the second release. I wanted to deploy it more in less gradient because it is obviously stuck first, but then it turns out to be interesting because this is maybe a 2-in-1 experiment. First, the bunch goes around an eddy, but later on it disperses in the region. Sorry for the green. Okay, this is the other one. Okay, finally, we did the analysis of the third order structure function. The red one is the one we knew from Benguela, and the blue one is from Walvis Ridge. And we have two different kinds of drifters. And what one can see is that although it's not as nice as the Benguela, there is a positive signal at the same scales as in Benguela, but with slightly different energy transfer rate. It was also a different season, but I do not know now why it's different. And the shallow drifter do not give a signal at this scale at all. So the shallow drifter with our cannot measure the inverse cascade, but when we zoom in, there might be some negative signs of the third order structure, like other people have found and might point to, forward cascade would be a bit too much because it's on these scales not really 3D turbulence, but that's something to discuss. But Kolmogorov have similarity. So, okay, the conclusion I gave already that both deep drifters showed a positive plateau with different energy transfer, and the shallow drifter not, but possibly Kolmogorov self-similarity. That means we should look at the PDFs. And the outlaw, we want to expand this drifter analysis to apply triangle method to receive kinematic properties, like in the collaboration with Yang Ping, from drifter groups which encircle the eddy. And we want to calculate the third order structure for smaller boxes with the goal to get a map of transfer rates, which is ambitious, I think, because and if that works, we would like to expand it to the global drifter program. Then there will be a third cruise, which will be during the Calvat phase of the SWOT. And finally, very important that is the reference, namely for the high resolution Walvis Ridge telescope model, we aim to derive both Lagrangian and Eulerian structure functions, because this is important to interpret the results, the drifter results. We did it PhD. Ilmar, he starts to do it for the for the Gulf Stream. Well, and then spectra, and we would possibly look at different path depths. Thank you.